Hello students, welcome to a new lecture of second year chemistry in which we are going to discuss a new chapter called as coordination compounds. And a coordination compound is a huge class of compounds in which we are going to discuss about the commonly known atoms only, but they are associating with each other in a different manner, right? To understand what is the behavior of coordination compound, we should first start with a basic salt which we know. Can you tell me the example of a basic salt? I am taking an example of NaCl, right? This is nothing but sodium chloride salt in which this is a solid salt, right? If I dissolve this solid salt in a glass of water, if I dissolve sodium chloride salt in water, immediately salt will be ionized into its respective ions. Upon dilution, sodium chloride gets separated in the form of Na plus ion and Cl minus ion, right? So this is the nature of a salt which gets dissociated in water to give ions, right? I will take an example of another salt like Morse salt. Right, this is an example of Morse salt. It is a salt in which there are two salts present together and hydrated. Along with water it is present, therefore it is called as hydrated salt of KCl and NgCl2. Therefore, this salt is called as a double salt. This salt is called as a double salt. Even though the structure of this salt is looking big, upon dilution, even this salt also dissociates and gives the ions which are possible, which is upon dilution this salt also gives cations separately and anions separately, right? Upon dilution, even this Morse salt, which is a double salt, also gets ionized to give its ions. This is the nature of a salt in which ions gets dissociated upon dilution. Now I will take an example of a coordination compound. Here I have taken an example of a coordination compound of copper complex, right? This is a coordination compound in which cation and anion is there, right? So when I dissolve this coordination compound in water, which ions are possible to get? In the total compound, you can see that there are 2 plus 1, 3 chloride ions and 1 Cu plus 3, right? 1 Cu plus 3 ion can be possible and 3 chloride ions can be possible. So which ions you should get on dilution is 1 copper plus 3 ion and 3 Cl minus ions you should get. But that is the speciality of coordination compounds, which says once the coordination compound is formed, they cannot be dissociated in the form of ions even if you add water. And whatever ions are entering inside the coordination sphere, the square bracket which I am telling here is a coordination sphere. Whatever ions are entering inside the coordination sphere are no longer called as ions. They become negatively charged ions, become ligands, and positively charged ion become central metal cation, central metal ion. Once they are entering inside the coordination sphere, you cannot call them as cation and anion. Then what you should call is anion is called as ligand and cation is called as central metal ion. And inside the coordination sphere, the total molecule behaves in a single manner and it shows a special characteristic which was not there before the coordination sphere was formed. Once they come inside the sphere, their identity completely changes. They are no more having the same property of Cl minus chloride ions. They are no more having the same property of Cu plus 3 copper cation. They behave differently, and that different compound is called as a coordination compound, which will not dissociate upon dilution, right? So, if you add water to this compound, you will get two type of ions. One ion is this ion called as chloride ions, and the other ion is this ion, which is one big coordination ion. The whole square bracket will be in the form of an ion called as positive ion. Inside the square bracket who was there will not come out whether you add water or whatever it is. Once they form, they are final. Their identity got changed after making a coordination compound, and they show different properties. Before coordination compound, their properties were different. Once coordination compound is formed, their properties are different, right? This special compound whose properties are different from a normal salt is called as a coordination compound, in which you will see a central metal ion surrounded by so many groups, right? What is the name of that group? What is the name of coordination sphere? And what is the charge of the coordination sphere? Let us study in detail, okay? But before going for that, I told that once the coordination compound is formed, their identity changes completely. What type of change occurs was given to us by Werner's theory. Werner in his theory told how the nature of the compound before forming coordination was different from after forming coordination, right? So, Werner's theory told us that coordination compound is not like a normal salt, it is different. What is the difference? Let us see. I will take the example of same coordination compound and explain whatever was told by Werner, right? According to Werner's theory, he postulated that coordination compound contains two type of valencies. One valency is called as primary valency, and the second type of valency is called as secondary valency. Second type of valency is called as secondary valency, right? When you come to primary valency, it means the normal ion which can be dissociated in water. That is nothing but primary valency. How many ions are coming out in water upon dilution is called as primary valency. In other words, you can also call it as the number of negatively charged ions present outside the coordination sphere is called as primary valency. I repeat, the number of negatively charged ions where should be present? The number of negatively charged ions present outside the coordination sphere is called as primary valency. In this compound, how many ions are present outside the coordination sphere is only one. Therefore, what is the primary valency of this compound is 1. In some cases, you may have two negatively charged ions present outside. In that case, its primary valency is 2. If 3 negatively charged ions are present outside the coordination sphere, its primary valency will be 3. And primary valency is always negative in nature. You cannot have neutral groups or neutral atoms getting counted for primary valency. In the compound which I have written here, along with Cl minus, you will have 2 water molecules also, because it will be hydrated, but you will not count all of them who are present outside the coordination sphere you will not count. What you count is only negative ions present outside the coordination. It should be negative, it should be outside the sphere. These two conditions you should look at. You should not count 3 molecules are present. One is for chlorine, water, total 3, primary valency is 3. No, you should not do like that. You should only see negative ions outside the sphere is only this. So, its primary valency is this. Coming to the secondary valency is the number of atoms or groups. The number of atoms or groups which are surrounded by the central metal ion is called as secondary valency. It can be in the form of an atom or it can be in the form of a group. How many like that are present around the central metal ion, and that atom or that group can be either negatively charged or neutral atom. Either negatively charged or neutral molecule. It can be anything of negatively charged or neutral, but where should be present? They should be surrounding the central metal ion, right? Any atom or any group who is surrounding the central metal ion is counted, and how many are present like that, that total will give you secondary valency. So, let me count in this case, and the condition of only negative is not there. It can be negative or even neutral. But for primary the condition was only negative, but for secondary that condition does not exist, right. So, in this case we have already counted that the primary valency was 1. Now, let us count secondary valency. What did I say? Definition was the groups or the atom or the group which are present surrounding the central metal ion is secondary valency. In this case, who is the central metal ion? Copper is the central metal ion. Who is surrounding the central metal ion is 4 molecules of ammonia is surrounding, and 2 atom of chlorine is surrounding. 2 chloride minus and 4 ammonia molecules, total 6 molecules, 6 groups are surrounding the metal ion, right. 1 Cl minus, another Cl minus, ammonia, 4 ammonias and 2 Cls together. 4 ammonias and 2 Cl minus are together surrounding the central metal ion in this example. Therefore, total how many groups are surrounding? 4 plus 2 is 6. The secondary valency of this coordination compound is 6, right. That means in this compound the 6 ligands are surrounding the central metal ion, and secondary valency is also called as coordination number of that coordination compound. How many secondary valency value you got? That is the coordination number of the given compound. So, for this given coordination compound, as the primary valency is 6, the coordination number is also 6, and secondary valency need not be always negative, need not be always neutral, it can be both neutral and negative. So, right, in this case what happens is primary valency is differentiated from secondary valency. So, now to make the primary valency and secondary valency clear, one more important point about these two is primary valency can be changed, but secondary valency of the compound cannot be changed. Primary valency of the compound can be changed, secondary valency of the compound cannot be changed, right. Once the secondary valency is 6, for this particular compound it should be 6 only, even if you take 3 chlorine, 3 ammonia or 5 ammonia, 1 chlorine or whatever it is, but the total value should be 6 only, because it cannot be changed. Whereas primary valency can be changed, secondary valency cannot be changed. One more point about them is primary valency can be ionized, means separate ion you can get. Secondary valency cannot be ionized in water. That means if primary valency can be separated in the form of ion, you can also precipitate them in the form of a precipitate. You can also separate them in the form of a precipitate by using a suitable reagent. To separate chloride as a precipitate, which reagent you should add? If you add AgNO3 reagent, what happens? Ag plus from AgNO3 and Cl minus from this compound, together they will make AgCl precipitate, and once the precipitate is formed, can you look at the precipitate? Yes. Precipitate is visible or not? Yes. So, if 1 mole of precipitate is formed, 1 mole of AgCl is formed, means only 1 Cl minus was there outside the sphere. If 2 moles of AgCl is formed, that means 2 Cl minus was present outside the coordination sphere. If 3 AgCl is formed, that means 3 chlorides are present outside the sphere. If you are not getting any precipitate of AgCl, that means either chloride ions are absent or they might be present inside the sphere. If they are present inside the sphere also, you cannot precipitate. That means outside the sphere they are absent, they might be inside the sphere but you cannot see, right. So, now let us look at 3 different complexes in which primary valency is changing. In which primary valency is changing. Or 3Cl. This is one complex. This is another complex. This is another complex. And this is the last complex. Right? These are all the complex in which number of chlorides used is only 3. To make the coordination compound, you need how many chlorines? Only 3. With that 3 chlorines and ammonia, you will get this complex in which what is the secondary valency of the coordination compound? Number of atoms or groups present inside the coordination sphere surrounding the central metal ion is called as secondary valency. Here 6 ammonias are present, therefore secondary valency is 6. What is the primary valency? Number of negatively charged ions present outside the coordination sphere is called as primary valency. In this case, 3 Cl minus ions are present outside the coordination sphere, therefore primary valency is 3. Coming to the next complex, secondary valency is 5 ammonias plus 1 chlorine, total secondary valency is 6. Whereas primary valency means number of negatively charged ions present outside the coordination sphere is called as primary valency, which is only 2. Coming to the next complex, 4 ammonias plus 2 chlorine, total is 6, secondary valency remains to be 6. Whereas primary valency is number of negatively charged ions present outside the coordination sphere is primary valency. Here you have only 1 Cl minus ions which is present outside the coordination sphere, primary valency is 1. Coming to the last complex, number of atoms or group surrounding the central metal ion is secondary valency 3 ammonia plus 3 chlorine, so secondary valency is 6. And primary valency, number of negatively charged ions outside the coordination sphere, no negative ions are present outside, therefore primary valency is 0. So let me go back to the earlier definitions. Primary valency can be changed but secondary valency will always be fixed. Primary valency can be ionized in the water, secondary valency cannot be ionized in water. If primary valency can be ionized, you can also convert that ions in the form of a precipitate. How can you get the precipitate of all the compound? Can you get the precipitate of AgCl by this compound? Yes. If you add AgNO3 to this, I am adding AgNO3 reagent to all the compounds, right? First compound utilizes how many AgNO3s? How many AgNO3s are utilized? You can tell by looking at how many Cl minus are present. If 3 Cl minus are freely present, freely means outside the sphere. If they are inside, you cannot call them free, they are fixed. Who is outside the sphere, they are only free. Who is inside the sphere are not free. So 3 Cl minus are freely present, therefore it can use 3 Ag plus ions to get 3 moles of AgCl precipitate. Second complex, when you give AgNO3 to the second complex, 2 Cl minus are freely present, so it utilizes 2 moles of Ag plus ion to give 2 AgCl precipitate. The next complex has only one free Cl minus ion, so it utilizes only one Ag plus ion to give 1 mole of AgCl precipitate, whereas the last complex, there is no free Cl minus ion outside the sphere, so it cannot give any precipitate of AgCl even though chlorines are present inside the sphere, but they cannot come out because they are fixed, right. So depending upon the number of precipitates you get, you can conclude if 3 precipitates you are getting, that means 3 ions are free. If 2 are coming, that means 2 ions are free. If 1 is coming, 1 ion is free. If nothing is coming, if there is no precipitate at all, that means there are no ions free, right. This is the conclusion by giving Werner's theory. You please read Werner's theory for 4 marks, it is very important, and here we will end today's lecture. Okay, thank you.